guys alive? Okay. All right. Let's just get started. Let's just end the day real quick. All right, let's just end the day real quick. Uh, for your sake and mine. So I see that most of you are good, right? Most of you are good. Most of you got it right. So, uh, flowing water. Based on last class, we said that flowing water was an analogy for current electricity, right? Basically, flowing electrons in a circuit, just like how water flows through a pipe or a river or a stream, electrons are flowing through a circuit. And you can think of that would be what analogy for flowing water, right? Current electricity. So let's move on. And so this is showing you a circuit board, right? This is showing you a circuit board. We have 16 of these at school. We have 16 of these in the lab, but you guys will never see it, which is unfortunate. Now, you might not see it, but this is like, okay, so let's take a look at the right-hand side. So it's a circuit, right? So this is a circuit on the right-hand side. It's a very simple circuit, rather. So it's a very simple circuit that allows electrons to flow through the wire. Right, allows electrons to flow through the wire. And you might not see it clearly in this image, but there are tiny lines that connect each of these. All right, there are tiny lines that connect each of these things that allow electricity to flow through. Actually, I think it's like this, actually, yeah. Right? So it might not be clear in the image, but it is clear when you see it up close. Anything that has electricity has a circuit. Your phone has a miniature motherboard in it, right? That kind of looks like this, except it's obviously the miniature version of a circuit board. Anything that pretty much runs on electricity has some sort of circuit board, right? Has some sort of it. Besides simple circuits, right? So simple circuits like this, if they're really simple, it's just like a battery and a circuit. But yeah. All right. All right. All right. All right. So it might not be clear on your end, guys. But let's see how it goes. What do you guys think is happening in the GIF?
The electrons are moving from left to right.
Oh, so it is clear. Okay, yeah, no, you're right. It's moving from left to right. It's moving from,
Higher potential to lower potential.
yes, that is the key thing. It's going from higher potential to lower potential. That's how electrons flow. Electrons go from high potential to low potential. If you don't have a potential difference, if there was no difference, you would not have a flow of electrons. You would not have a flow of electrons. So, and yesterday we compared voltage to water pressure. How do we compare? Using these images, I want you to take like 2, 3, 5 minutes. How would you compare voltage to water pressure? And use these images as like a hint. I'm gonna write down, I'm gonna give you a hint, right? So the battery, you can think of a pump as a battery, right? You can think of a pump as a battery. Oh man. Jesus, 80 degrees. You got to go pick up your little brother now, sure. It seems like you didn't answer anything at all, so you're still getting a 0 for classwork. You didn't even answer the first question. So you're still getting a 0. I mean, how could you not answer the first question? We did. You don't understand. Didn't we talk about electrons and water pressure of how it flows? Yeah, we did. I mean, you answered number 2 and your answer to number 1. Your answer to number 1 was essentially your answer to number 2. Question 1 was asking what would you compare flowing water to? And the only answer there was, the only thing you needed to the right was current electricity. Like flowing water was basically flowing electrons in a circuit. Yeah, that your answer to number 1 it should have been the answer to number 2. I mean, you can just copy paste. The system will flag you copy pasting, but it's fine. I know. I know you did. All right. All right, let's take a look. Let's get a look at your answers. I mean, it's not too well. It's not going too well. Some of you guys didn't really answer. So let's go over it, right? So again, let's just focus on the water pressure part. How is this water flowing? How is water gonna flow?
Like some of the water that's like some of the water is gonna move to like the lower pressure area to balance it out.
What do you
Yeah.
mean by like water flow?
What do I mean by water flow? The movement of water.
In like a specific direction?
Yes.
Like affect something?
It's just in general, the movement of water. It really isn't a direction. It's just like the movement of water.
Alright, I see, I see.
Yeah, what question am I going over? Your internet was buffering. I'm going over question 2. So water goes from high pressure to lower pressure. I think most of you are okay with that, right? Most of you are okay with water going from high pressure to low pressure. But you can just think of voltage the same exact way, because if you think of voltage as well, if you have a lot of electrons over here, right? You have a lot of electrons over here. Well, these electrons don't want to be anywhere near each other. Well, where are they going to go? Well, they're going to go to an area that has lower pressure, right? There's lower electric pressure there. So you're essentially going from high potential, right? There's high potential, there's high electric potential, and you're basically going to lower potential. You're going to lower electric potential. Right, there's more electrons there, so there's a higher electric potential, right? Because they're basically all pushing against one another. And then you're going to go in the area with lower potential. So just like how water goes from high pressure water to low pressure water, voltage is the flow of electrons from high potential to low potential. All right, just like how water goes from high pressure to low pressure, voltage is the same way. Electrons go from high potential to low potential. So again, water goes from high pressure to low pressure. And electrons behave the same way. They go from high potential to low potential. And because there is a potential difference here, right? There is a difference in potentials, which is why you have a flow of electrons in the first place, which is why electrons are moving, which is why you have electricity. In very simple electric circuits, right? Your battery supplies that potential difference, right? The battery creates a potential difference, right? There's more electrons on one side, which means there's more electric potential on one side. And so the battery creates a flow of electricity. Anyway, let's take a look at this image right here. I think this image is really good analogy. Think of a circuit and an appliance like a dam, right? You're running electricity through something. But you need a potential difference. So your potential difference is supplied by the fact that you have a high voltage somewhere. Let me just use a different color. All right, let me use a different color. Sure, red is always the best, to be honest. So let's say you have a lot of electrons here, right, on the top, and you're basically, there's a lot of pressure. There's a lot of electric pressure. There's a lot of electric pressure here. And at the bottom, you don't have as much pressure, right? There's less electrons at the bottom. There's less electrons at the bottom, is lower voltage, lower pressure. Well, what's going to happen is that the electrons are going to go from high voltage to low voltage, right? It's going to go from high voltage to low voltage. And it's the fact that there is a difference here, right? There's a potential difference, right? There is a potential difference. Remember, voltage is basically electric potential. And because there is a potential difference here is the reason why you have electricity, which is why you have a flow of electrons. And now, but appliances themselves don't it can slow down the rate of electric flow. Right, even though the water is like flowing through this dam. Whatever appliance you are running the electricity through, it can slow down the rate at which the water flows, right? Or rather the electrons flow. So a dam, this middle part right here can act like, you can think of it as like a resistance. All right. I think the easiest example to show you guys is to talk about it like this. I think of it like this. You guys are obsessed with your phones. So let's draw a phone. Let's use a phone. Let's say your phone is at 10%. And this is at nothing at all like what a battery looks like. Please, this is not a realistic drawing of a battery. All right, this is not a realistic drawing of a battery. So let's say you have 10% battery left and you have the electrons, you have that many electrons left over. And let's say the voltage is, I don't know, let's say it's 10, actually. Sure, I'm just gonna make it simple, 10 volts. I'm just gonna match the percentage to the voltage. You know what? Makes it easy. And now you're connecting your phone to a charger, right? So you're connecting your phone to a charger. So you're connecting your phone to a charger. And the wall outlet is rated at a voltage of 120. So let's just use 120. Even though it's actually, let's just lower to 100. So your phone, it rates at 100 and the voltage is coming in at 100 volts. Your phones, it depends on what type of material or appliance you have. Certain appliance will limit the voltage because you don't want your entire appliance breaking due to too high of a voltage. And so there's a voltage difference here, right? There's a potential difference here. There's a potential difference of 90 volts. And as long as you have a difference, your phone will charge, right? Your phone will start charging if there's a potential difference here, which lets electrons flow. Now, let's say a while later, your battery is now 40%, and let's say the voltage of your battery is 40 volts now. Yeah, only 12 volts. It's probably, yeah, that's correct. That's probably true. But again, this is like a hypothetical situation. I'm saying like things limit the amount of volts that you get. Right? You don't want the entire 120 volts or your thing is going to break. If it's a certain appliance, right? Your phone, your charger is not going to give you, it shouldn't give you, it should not give you 100 volts. That's too much. But this is a hypothetical. This is a hypothetical. This is not real. So again, you charge it to 40% and it's 40 volts now. And there's a pressure difference, right? There's a potential difference of 60 volts. Well, because there's less difference, your electrons are still going to flow through. But what do you think happens to the speed at which electricity flows? Compared to before, compared to when it was 10%, and your potential difference was 90 volts, right? Compared to before when it was 90 volts, and your battery was at 10%, what do you think happens to the speed at which your phone is charging? What do you guys think if I made this dam even smaller? Actually, I don't even care. Maybe that's resistance. No, that wouldn't be a good analogy. Guys, if you think about it, I'm sure you've seen it. When you've gotten to like 80% battery, you've noticed that your phone starts charging slower. Right? Because then look at the difference here. Look at your potential difference. As you get to a higher percentage of charge, your voltage increases and your potential difference, right? The difference in potential decreases as well. And because your potential difference decreases, the rate at which your phone is going to charge is going to be much slower. Right? Because there's more electrons here now. Right? There's more electrons here now, and they don't want more electrons. Right? The battery doesn't want more electrons. They don't want to see them at all. They don't want new electrons because there's too much of it here already. But as long as there's a potential difference, as long as you have a difference in potential, you have flowing electrons. This is basically how basic electricity works. Basic electricity works because you have a potential difference. So you have a flow of electrons. Yeah, it's going to slow down. The rate of charge will slow down. Anyway, let's do number 3. There are 2 things I want you guys to notice here. So let's start with the context. So you have a battery. You have something that measures current, goes to the battery. And you see a copper wire over here. There's a copper wire over here that conducts electricity. And there's another wire that connects back to the circuit. Connects back to the battery. What do you notice happens to the thermometer, right? There's a thermometer connected to the wire. What do you notice about the temperature? And what do you notice about your current? The temperature increases, okay. And what else? What happens as your temperature increases? The current decreases. Yeah. So as time goes on, guys, as you keep running an electric current through something, the temperature increases. But because the temperature increases, your current, your electric current, the rate at which electrons flow through a wire decreases. Think about it, guys. Your phone gets hot, right? Your charger gets hot when it charges because you have electrons creating friction as it bumps through all the atoms and material. Yes, is number 3. All right. Also, something about number 3 before you answer it is there are 2 things here. There's something called resistance, and there's something else called resistivity. Right? These are 2 separate things. There's something called resistance, and there's something called resistivity. Resistivity is basically the material, a measure of the material's innate resistance to transfer electrons, right? It's basically every material can transfer electrons with different resistances. So that's really the difference. Resistance is just like of the whole wire in general, but resistivity is only the material. So the only thing you need to write for number 3 is that the higher temperature, the hotter you get, the hotter the wire gets, the harder it is for electrons to move. So higher temperature, lower current. Higher temperature, lower current.
Sorry, can you repeat that?
Higher temperature, lower current.
That's all for 3.
And because there's a lower current, that means higher resistance.
Wait. Higher
All right, all right.
temperature, lower.
Current is I, by the way. I is current. And R is resistance. All right. And I can assume that you guys know what T means, all right? Please tell me you guys know what T means.
Can you say it in words again, what you said before?
Yeah, higher temperature, lower current, higher resistance. Ah. All right, let's finish this off with a video. All right.
In this segment of Physics in Motion, we're going to talk about Ohm's law. Ohm is the last name of a German physicist and mathematician who back in the 19th century solved a mystery that led to major advances in our ability to use electricity safely and reliably. Ohm figured out how 3 basic aspects of electricity relate to each other. Knowing how these 3 properties affect each other is what lets engineers design circuits, the paths that we use to send electricity where we want it to go and do. The 3 properties that Ohm studied are voltage, current, and resistance. Let's break it down. Voltage is the difference in electrical potential between 2 points. It's like the pressure of a water pump pushing current through a loop, so the charge can be used to do work. Current is the rate at which charge is flowing in a circuit, similar to water flowing through a channel. Resistance is a material's tendency to resist the flow of charge or current, like rocks or sticks blocking a channel of water. And if you know 2 of these 3, you can figure out the last one using the law Ohm discovered. So what Ohm did back in the 1820s was to record a lot of data measuring different voltages and wire lengths, which led to his discovery about their relationship. In his day,
So there's something named amps. Yeah, ampere. Ampere. It's short. Amps is short for ampere.
the materials used in these experiments were handmade and not very exact, so results varied. Scientists like Ohm were working with early forms of batteries and wires, but
And resistance is measured in ohms, which is named after the scientist, the physicist.
Ohm worked hard to make his work consistent and easy to replicate so that he knew his data were correct. After years of work, he felt he had proof of something that people had been unsure about. The longer the wire he used in his experiments, the less current flowed through it. That was because resistance increases as the wire becomes longer. That's important because it helps us to understand how much electrical power is being used in the system. The higher the resistance, the more heat is generated. In the case of an old school incandescent bulb, the heat makes the filament shine brighter, for instance. It may seem simple now, but it was a breakthrough. Today we can measure voltage, current, and resistance with this, a multimeter. Let's do a simple circuit test. A circuit, which you'll hear more about later on in this unit, is a closed loop through which electrical charge can continuously flow. We'll make our circuit with a battery, some wire, a light bulb, and a resistor. When we connect the circuit, that means I connect this wire here. And the loop is closed, the bulb lights up. Now, let's find out what the current is in the resistor and also measure its resistance. If we connect a multimeter into the circuit, like this, we can make it measure current, which is expressed in amps. And it's reading out 176 milliamps, or 0.176 amps. Now, if we change the multimeter settings, we can measure the resistance in a unit called ohms, named after our guy George. And it looks like the resistor's resistance is 1.5 ohms. By Ohm's law, when we multiply these two together, we get the calculated voltage of 0.26 volts. In Ohm's day, measuring what we just did would have been much more difficult. But with modern equipment, it's relatively easy. We can do a little something similar to what Ohm did when he spent all that time recording data. Let's measure the currents of some wires of different materials and lengths. Here's copper, aluminum, and steel, using our trusty multimeter. Let's hook up the leads.
You know, you guys don't really need to pay attention to this because you're not really learning about the formula, but it's nice to hear.
See what we get. And then we'll fill in the points on our graph of voltage versus current, like this, adding the measurements for each material. When we look at the ratio of the current to the voltage, we see that when current changes, the voltage changes. And within each type of metal, the straight line tells us the ratio is about the same. That's the basic principle that Ohm discovered. His work led to the realization that current through a conductor, like the metals seen in this graph, is directly proportional to the voltage across the same span of wire. The ratio of voltage to current, the slope of these lines, is equal to the resistance through the wire. The more recognizable version of his law looks like this. Voltage equals current times resistance. There are a few exceptions to Ohm's law. Not all materials are ohmic, meaning they don't follow Ohm's law. Their voltage and current aren't related in the same way as other materials. Doubling one doesn't necessarily double the other. An example of a non-ohmic material is an LED light. It can use much smaller current to provide the same light as an old-fashioned filament bulb, saving energy. Even though not all materials follow Ohm's law, it's still used by electrical engineers all over the world. One more thing about Ohm. When he first published his findings about electrical resistance in 1827, the reaction was so bad among the thought leaders of the day, he quit his job. It was almost 15 years before he was recognized for his work that changed the world. It's a good lesson in sticking with things, as well as a lesson on how to analyze electrical circuit. That's it for this segment.
Give me a second, guys. Setting something up. Guys, you should stick with something only if you have evidence. Don't stick with something when you have nothing to show for it. All right. Anyway, see you guys tomorrow. See you guys tomorrow.